Space has always captivated the imagination of humans. It's a realm where mysteries abound, where phenomena defy expectations, and where our understanding is constantly challenged. One planet that often escapes the limelight, overshadowed by the grandeur of giants like Jupiter and the beauty of Saturn, is Mercury. Yet, in its own way, Mercury is a mystery-filled world that holds secrets waiting to be uncovered. As the closest planet to the Sun, Mercury's extreme conditions, peculiar behaviors, and enigmatic composition present questions that even the most advanced scientific minds struggle to fully answer. But before we continue, if you like this type of videos, please subscribe to the channel and comment. Today, we're going to dive into the many facets of Mercury, exploring its place in the cosmos, its history, and the mysteries that continue to perplex scientists. But first, imagine a world so close to the Sun that temperatures soar to unbearable heights during the day, yet plummet to freezing lows at night. Imagine a place where a single day lasts nearly 2 Earth months, and where the surface is pockmarked with craters from ancient impacts. A place where the gravitational forces from the Sun are so powerful that they tug at the planet's very core. This is Mercury, a planet of contrasts and contradictions, a celestial body that defies easy explanation. While it's often thought of as a relatively plain planet, lacking the dramatic rings of Saturn or the sprawling storm systems of Jupiter, Mercury's subtle complexities reveal a much more fascinating world. Its orbit is eccentric, its rotation is unlike any other planet, and its geological history is etched into its surface. From the vast craters marking its face to the strange hollows dotting its plains, Mercury is filled with puzzles. And at the heart of these puzzles is one lingering question: how did Mercury, a small, rocky planet so close to the Sun, come to be the way it is? The journey to understanding Mercury begins with its formation billions of years ago, during the early days of our solar system. Like the other rocky planets, Mercury was born from the swirling disk of gas and dust that encircled the young Sun. However, Mercury's proximity to the Sun set it apart from the start. The intense heat and radiation from the Sun likely stripped away much of the planet's lighter elements during its formation, leaving behind a dense, iron-rich core surrounded by a relatively thin mantle and crust. In fact, Mercury's core makes up a larger proportion of its total mass than any other planet in the solar system, and understanding why this is the case is one of the enduring mysteries of the planet. One theory suggests that Mercury may have once been much larger, but early in its history, it was struck by a massive object that stripped away much of its outer layers, leaving behind the dense core we see today. This catastrophic event would explain Mercury's unusually high density and thin crust, but it's just one of several hypotheses scientists have put forward to explain the planet's current state. Mercury's orbit is another peculiar feature that has puzzled astronomers for centuries. Unlike the more circular orbits of Earth or Mars, Mercury's orbit is highly elliptical, meaning that it varies dramatically in distance from the Sun. At its closest point, Mercury is just 46 million kilometers from the Sun, while at its farthest, it's nearly 70 million kilometers away. This eccentric orbit means that Mercury experiences intense variations in temperature. During the day, temperatures on the planet's surface can reach a scorching 430 degrees Celsius, but at night, when the Sun sets and the planet's thin atmosphere does little to retain heat, temperatures can plummet to as low as -180 degrees Celsius. This extreme temperature fluctuation is one of the most striking aspects of Mercury, and it has a profound effect on the planet's surface. Over billions of years, the constant heating and cooling have caused Mercury's surface to contract, creating long, steep cliffs known as scarps, that can stretch for hundreds of kilometers. These scarps are among the most distinctive features on Mercury's surface, and they provide important clues about the planet's geological history. But Mercury's orbit holds more mysteries than just its shape. For centuries, astronomers struggled to explain a strange phenomenon known as the precession of Mercury's orbit. This refers to the way the point at which Mercury is closest to the Sun shifts slightly with each orbit. While the gravitational influences of other planets, particularly Venus and Jupiter, account for some of this precession, they don't explain all of it. In the 19th century, this discrepancy led some scientists to propose the existence of a hypothetical planet, dubbed Vulcan, that was thought to orbit even closer to the Sun than Mercury and exert an additional gravitational pull. However, Vulcan was never found, and the mystery remained unsolved until the early 20th century, when Albert Einstein's theory of general relativity provided the answer. According to Einstein's theory, massive objects like the Sun warp the fabric of spacetime, causing nearby objects to move in ways that Newtonian physics couldn't fully explain. The precession of Mercury's orbit was one of the first major confirmations of general relativity, and it remains one of the most important pieces of evidence supporting the theory. Yet, even with this mystery solved, Mercury continues to surprise scientists. One of the most recent discoveries is the presence of water ice in permanently shadowed craters near Mercury's poles. Despite the planet's scorching daytime temperatures, these deep craters never see sunlight, allowing ice to remain frozen in their depths. This discovery was made possible by NASA's Messenger mission, which orbited Mercury from 2011 to 2015, providing the most detailed images and data ever collected about the planet. The discovery of water ice on Mercury raises intriguing questions about how it got there. One possibility is that it was delivered by comets or asteroids that impacted the planet over billions of years. Another possibility is that water molecules from the solar wind, a stream of charged particles emitted by the Sun, could have combined with elements in Mercury's surface to form ice. Either way, the presence of water ice on such a hot, inhospitable planet is a reminder that Mercury is far more complex than it appears at first glance. As we delve deeper into Mercury's mysteries, it's important to remember that our understanding of this planet is still evolving. Despite being one of the closest planets to Earth, Mercury remains one of the least explored. Only two spacecraft, Mariner 10 in the 1970s and Messenger in the 2000s, have visited the planet, and much of its surface remains unexplored. One of the next great steps in Mercury exploration is the European Space Agency's BepiColombo mission, which launched in 2018 and is set to arrive at Mercury in 2025. This mission aims to study Mercury's magnetic field, surface composition, and interior structure in greater detail than ever before. With the data from BepiColombo, scientists hope to answer some of the remaining questions about Mercury's formation, its geological history, and its place in the broader context of the solar system. But even as we look to the future, Mercury's past continues to offer tantalizing clues. The planet's surface is covered in impact craters, evidence of a violent history filled with collisions from asteroids and comets. Some of these craters are ancient, dating back billions of years to the early days of the solar system, while others are more recent, offering a glimpse into the ongoing processes shaping Mercury's surface. One of the largest and most famous craters on Mercury is the Caloris Basin, a massive impact structure over 1,500 kilometers in diameter. The impact that created the Caloris Basin was so powerful that it caused shock waves to ripple through the planet, creating a chaotic region of hills and valleys on the opposite side of the planet known as the Weird Terrain. In addition to its craters, Mercury's surface is also home to a number of enigmatic features known as hollows. These bright, irregular depressions appear to be relatively young, and they're unlike anything seen on other planets in the solar system. Scientists aren't entirely sure how the hollows formed, but one theory is that they're the result of volatile materials, such as sulfur, sublimating, turning from a solid directly into a gas, under Mercury's harsh conditions, leaving behind these strange depressions. Despite its small size, Mercury has a surprisingly strong magnetic field, another mystery that scientists are still trying to understand. Most planets generate magnetic fields through the movement of molten metal in their cores, but given Mercury's small size and its proximity to the Sun, it was expected that its core would have cooled and solidified long ago. However, data from the Messenger mission revealed that Mercury's core is still at least partially molten, allowing it to generate a magnetic field, though it's much weaker than Earth's. This magnetic field interacts with the solar wind, creating a dynamic and constantly changing environment around the planet. Mercury's magnetosphere, the region of space influenced by its magnetic field, is constantly bombarded by solar particles, leading to frequent magnetic storms that are far more intense than those experienced on Earth. Understanding how Mercury's magnetosphere operates could provide important insights into the behavior of magnetic fields on other planets, including Earth. The mysteries surrounding Mercury's magnetic field and magnetosphere are particularly fascinating because they challenge our understanding of how small planets, particularly those so close to the Sun, can maintain such dynamic internal processes. Mercury's magnetic field is thought to be generated by the movement of liquid iron in its outer core, much like Earth's. However, Mercury's field is much weaker and offset from the planet's center, a peculiar characteristic that raises questions about how its core behaves. One of the leading theories is that Mercury's core is partially solidified, with a thin outer shell of molten iron still moving and generating the magnetic field. This theory is supported by the planet's density and the data collected by the MESSENGER mission, which found that Mercury's core takes up about 85% of its radius, much larger than any other planet in the solar system. This core size might explain the planet's unique magnetic characteristics, but it also raises further questions. Why has Mercury's core remained partially molten while other small planets, such as Mars, have cooled completely? There is also the intriguing possibility that Mercury's magnetic field could be influenced by external factors, particularly its proximity to the Sun. The intense solar radiation and solar wind that bombard Mercury may play a role in maintaining or modifying its magnetic field, though exactly how this happens is still a subject of research. One thing is clear: Mercury's magnetic field is not static. It is constantly interacting with the Sun's solar wind, creating a magnetosphere that, while smaller than Earth's, is incredibly dynamic. Within Mercury's magnetosphere, the constant flow of charged particles from the Sun generates powerful magnetic storms, some of which are intense enough to alter the planet's surface. These magnetic storms also produce bursts of X-rays, a phenomenon that has been observed by Earth-based telescopes. Understanding how Mercury's magnetosphere works could provide important insights into the magnetic environments of other planets, especially those that are similarly exposed to the Sun's powerful solar wind, like Venus and Mars. Yet another mystery surrounding Mercury lies in its rotational dynamics. Mercury's day, defined as the time it takes for the planet to rotate once on its axis, lasts for about 59 Earth days. However, Mercury's year, the time it takes to orbit the Sun, is only 88 Earth days. This means that Mercury experiences a phenomenon known as spin-orbit resonance, where the planet rotates 3 times for every 2 orbits around the Sun. As a result, a single day on Mercury, from one sunrise to the next, lasts for 2 Mercury years, or about 176 Earth days. This unusual rotational pattern is the result of gravitational interactions between Mercury and the Sun, and it makes Mercury one of the few planets in the solar system to experience such a unique synchronization between its rotation and its orbit. This 3:2 resonance has profound effects on Mercury's surface environment. For instance, it creates extreme temperature variations, as certain regions of the planet are exposed to the Sun's intense heat for long periods of time, while others are left in shadow for extended stretches. These conditions have shaped Mercury's surface, influencing its geological processes and possibly contributing to the formation of the mysterious hollows and scarps that cover the planet. Another significant effect of Mercury's spin-orbit resonance is the impact on its tidal forces. Tidal forces are the result of the gravitational interaction between a planet and its star, in this case, Mercury and the Sun. These forces are responsible for stretching and squeezing the planet, creating internal friction that generates heat. On Earth, tidal forces from the Moon contribute to phenomena such as ocean tides, but on Mercury, the Sun's powerful gravitational influence causes the planet to experience tidal locking. This means that over time, the same side of Mercury will always face the Sun during certain parts of its orbit, contributing to its extreme temperature contrasts. One of the more bizarre consequences of Mercury's orbit and rotation is that if you were standing on the surface of the planet in the right location, you could witness the Sun rise, then briefly set, and then rise again, all within a short period. This phenomenon occurs because Mercury's orbital speed changes as it moves closer to and farther from the Sun near perihelion. When the planet is closest to the Sun, its orbital velocity increases, causing it to briefly outpace its own rotation. This unique dance between the planet's orbit and rotation is just one more example of Mercury's complex behavior, which continues to intrigue astronomers. Mercury's surface, with its mixture of craters, plains, and mysterious hollows, is a geological record of billions of years of history. One of the most significant features of this surface is the Caloris Basin, an immense impact crater that spans over 1,500 kilometers in diameter. The Caloris Basin is thought to have been formed by a massive asteroid impact early in Mercury's history, and it is surrounded by concentric rings of mountains, the tallest of which rise nearly 3 kilometers above the surrounding plains. The impact that created the Caloris Basin was so powerful that it not only created the basin itself but also caused seismic waves to travel through the planet's interior, forming the weird terrain on the opposite side of the planet. This weird terrain consists of a chaotic jumble of ridges, valleys, and hills, all crumpled and deformed by the shockwaves from the Caloris impact. Understanding how this terrain was formed provides insights into the internal structure of Mercury, particularly the composition of its crust and mantle. The weird terrain also suggests that Mercury's surface was once much more geologically active than it is today, with volcanic eruptions and tectonic movements shaping the planet over billions of years. Speaking of volcanism, Mercury's surface is also dotted with vast plains that were formed by ancient volcanic activity. These plains, known as smooth plains, cover about 40% of the planet's surface, and they are thought to have been formed by the outpouring of lava from the planet's interior. Some of these volcanic plains are relatively young, indicating that Mercury may have been volcanically active much more recently than previously thought. This discovery challenges the traditional view that Mercury is a geologically dead planet and raises questions about the thermal evolution of its interior. The volcanic history of Mercury is closely tied to the planet's shrinking surface. As the planet cooled over time, its iron core contracted, causing the surface to crumple and form the long, steep cliffs known as scarps. These scarps, some of which are hundreds of kilometers long and over a kilometer high, are evidence that Mercury has shrunk by as much as 7 kilometers in diameter over its history. This process, known as global contraction, is unique to Mercury among the rocky planets, and it provides important clues about the planet's internal structure and thermal history. Mercury's geological history is also linked to its exposure to the sun's intense radiation. The solar wind, a stream of charged particles emitted by the sun, constantly bombards Mercury's surface, stripping away its atmosphere and eroding its surface features. Over time, this process has created a thin layer of space weathering on the planet's surface, darkening it and giving it a distinctive hue. This weathering is one reason why Mercury appears so dark and featureless from a distance, but up close, its surface is a rich tapestry of craters, plains, and mysterious formations. The study of Mercury's surface in geology has been greatly aided by the data collected from spacecraft missions, particularly NASA's Messenger mission. Launched in 2004, Messenger became the first spacecraft to orbit Mercury, and it provided unprecedented views of the planet's surface, magnetic field, and chemical composition. The mission revealed that Mercury's surface is rich in elements such as sulfur and potassium, which are surprising given the planet's proximity to the Sun. These volatile elements are easily vaporized at high temperatures, so their presence on Mercury suggests that the planet's history may have been more complex than previously thought. In addition to its surface features, Messenger also provided valuable data about Mercury's exosphere, a thin, tenuous layer of gases that surrounds the planet. Mercury's exosphere is constantly replenished by particles from the solar wind, as well as by gases released from the planet's surface through a process known as surface-bound exosphere generation. This process occurs when high-energy particles from the Sun collide with Mercury's surface, causing atoms and molecules to be knocked loose and escape into space. While Mercury's exosphere is incredibly thin, about 1 trillion times thinner than Earth's atmosphere, it still plays a crucial role in the planet's interaction with the Sun and the solar wind. The composition of Mercury's exosphere is also intriguing. It contains elements such as hydrogen, helium, sodium, and oxygen, as well as trace amounts of other gases. These elements come from a variety of sources, including the solar wind, impacts from micrometeoroids, and the planet's own surface. By studying Mercury's exosphere, scientists hope to learn more about the processes that shape planetary atmospheres and how they evolve over time. As we continue to explore Mercury, both from Earth and through future space missions, the planet's mysteries only deepen. From its unique rotational dynamics to its complex geology, magnetic field, and exosphere, Mercury is a world that defies simple explanations. The more we learn about Mercury, the more questions arise, challenging our understanding of planetary science. One of the biggest mysteries that remains unsolved is how Mercury came to be so dense. Mercury is the second densest planet in the solar system, after Earth, with a density of 5.43 grams per cubic centimeter. This is unusual for a planet so small. Mercury's mass is only about 5.5% that of Earth. Most models of planetary formation suggest that smaller planets should have lower densities because they are composed of lighter materials. Yet, Mercury defies this trend. Several hypotheses have been proposed to explain Mercury's anomalous density. One of the leading theories is that Mercury originally formed as a larger planet, but a massive collision early in its history stripped away much of its lighter, outer material. This catastrophic event would have left behind a planet dominated by its heavy, metal-rich core. Evidence for this theory comes from computer models of planetary formation, which show that such an impact could indeed create a planet like Mercury. However, the exact details of this impact remain speculative, and no definitive evidence has been found to confirm this theory. Another theory suggests that Mercury's proximity to the Sun played a crucial role in its formation. In the early solar system, the intense heat and radiation from the young Sun may have vaporized the lighter elements on Mercury's surface, leaving behind only the denser, metallic components. This theory, known as the solar evaporation hypothesis, provides an alternative explanation for Mercury's high density, though it too faces challenges. For example, if the Sun's heat was powerful enough to vaporize lighter elements on Mercury, why didn't the same process occur on Venus, which is also close to the Sun but has a much lower density? The debate over Mercury's formation and its high density is further complicated by the discovery of volatile elements on its surface. The MESSENGER mission detected high levels of sulfur, potassium, and other volatile compounds, which are usually not found in large quantities on planets that formed close to the Sun. These elements are easily vaporized at high temperatures, so their presence on Mercury seems contradictory to the solar evaporation hypothesis. If Mercury had experienced intense heating in its early history, these volatiles should have been lost. Their presence suggests that Mercury's formation and history may have been much more complex than previously thought. In addition to its unusual density, Mercury also has an abnormally large core relative to its size. Mercury's core makes up about 85% of the planet's radius, which is far larger than Earth's core-to-radius ratio. This has led some scientists to speculate that Mercury's core may contain exotic materials or elements that are rare in other planets. For example, some models suggest that Mercury's core could be enriched with sulfur or other elements that lower the melting point of iron, allowing the core to remain partially molten despite the planet's small size. These theories remain speculative, however, as we still lack direct data on the composition of Mercury's core. One of the most striking features of Mercury's surface is its extensive system of scarps, or cliffs, which crisscross the planet. These scarps are thought to be the result of global contraction, a process in which Mercury's interior cools and shrinks, causing the surface to buckle and form steep cliffs. Some of these scarps are hundreds of kilometers long and rise over a kilometer above the surrounding plains. The scarps are relatively young in geological terms, suggesting that Mercury's interior is still cooling and contracting today. This ongoing process makes Mercury one of the few planets in the solar system that is still geologically active. The presence of these scarps also raises questions about the planet's tectonic history. While Earth's surface is shaped by plate tectonics, Mercury lacks the large-scale plate movements that drive geological activity on our planet. Instead, Mercury's tectonic activity seems to be driven entirely by the planet's internal cooling and contraction. This has led some scientists to describe Mercury as a one-plate planet, where the entire surface behaves as a single, rigid plate that responds to internal forces. Understanding how this process works on Mercury could provide valuable insights into the evolution of other rocky planets, particularly those that lack plate tectonics. In addition to its scarps, Mercury's surface is also marked by a vast array of impact craters. Mercury's proximity to the Sun means that it has been bombarded by comets, asteroids, and micrometeoroids throughout its history. Some of these impacts were so powerful that they reshaped the planet's surface, forming enormous basins like the Caloris Basin. However, unlike the Moon, which has a similarly cratered surface, Mercury's craters are often filled with smooth plains, indicating that volcanic activity has played a significant role in resurfacing the planet. These volcanic plains, which cover about 40% of Mercury's surface, are evidence of widespread volcanic activity in the planet's past. Some of the smooth plains are thought to be the result of lava flows that occurred early in Mercury's history, while others may be more recent. The discovery of relatively young volcanic features on Mercury challenges the traditional view that the planet is geologically dead. In fact, there is growing evidence that Mercury may have experienced volcanic eruptions as recently as 1 billion years ago, long after the planet's initial formation. This raises the question of whether Mercury could still be volcanically active today. While no active volcanoes have been observed on Mercury, the discovery of relatively young surface features suggests that the planet's interior may still be capable of producing volcanic eruptions. If so, this would make Mercury one of the few planets in the solar system that is still geologically active, along with Earth, Venus, and possibly Mars. Mercury's volcanic history is also closely linked to its magnetic field. The planet's magnetic field is generated by the movement of liquid iron in its outer core, and this dynamo process is thought to be driven by heat generated from the cooling of the core. As the core cools, it releases heat, which causes the liquid iron to circulate and generate a magnetic field. However, Mercury's magnetic field is much weaker than Earth's, and it is offset from the planet's center, suggesting that the core may be cooling unevenly. The weak and offset nature of Mercury's magnetic field raises important questions about the planet's internal structure and the dynamics of its core. One possibility is that Mercury's core is only partially molten, with a thin layer of liquid iron surrounding a solid inner core. This would explain why the magnetic field is weaker and more asymmetric than Earth's. Alternatively, the offset magnetic field could be the result of complex interactions between the core and the surrounding mantle, which may be influencing the way heat is transferred within the planet. The study of Mercury's magnetic field is not only important for understanding the planet itself but also for gaining insights into the magnetic fields of other planets. For example, Venus, which is similar in size and composition to Earth, lacks a global magnetic field altogether. Mars, on the other hand, has only remnant magnetism from its past, while Earth has a strong and stable magnetic field. By studying Mercury, scientists hope to learn more about the processes that drive planetary magnetism and why some planets maintain magnetic fields while others do not. One of the most tantalizing questions about Mercury is whether it could harbor water. For a planet so close to the Sun, the idea of finding water seems far-fetched. However, in 2012, the Messenger spacecraft made a startling discovery, evidence of water ice in permanently shadowed craters near Mercury's poles. These craters are located at the planet's poles, where the Sun's rays never reach, creating cold traps that can preserve ice for billions of years. The discovery of water ice on Mercury raises exciting possibilities for the planet's history and future exploration. The presence of ice suggests that comets or asteroids, which are rich in water, may have impacted Mercury in the past, delivering water to the planet's surface. Alternatively, the water may have come from Mercury's interior, released through volcanic activity or outgassing. Either way, the presence of ice indicates that Mercury may have a more complex history than previously thought. The potential for water ice on Mercury also has implications for future missions to the planet. Water is a critical resource for space exploration, and if ice can be harvested from Mercury's poles, it could provide a valuable source of water for future human missions. This would make Mercury an important target for future exploration, as it could serve as a base for missions deeper into the solar system. Another intriguing possibility is that Mercury's ice may contain clues about the early solar system. The ice in Mercury's polar craters is thought to be billions of years old, and it may contain pristine samples of water from the early solar system. By studying this ice, scientists could learn more about the composition of comets and asteroids that bombarded the inner planets during the solar system's formation. Despite the harsh conditions on Mercury's surface, the discovery of water ice has led some to speculate about the possibility of life on the planet. While it seems unlikely that life as we know it could exist on Mercury today, the presence of water raises the question of whether the planet could have supported life in the distant past. If Mercury had a thicker atmosphere and more stable surface conditions in its early history, it's possible that microbial life could have existed in its ancient oceans or volcanic environments. The speculation surrounding the potential for life on Mercury, while far-fetched, is a compelling thought experiment. Although the planet's extreme conditions today, its blistering temperatures, lack of a substantial atmosphere, and intense solar radiation, seem inhospitable to life as we know it, there may have been a time in Mercury's distant past when the planet was more Earth-like. If Mercury had a thicker atmosphere or a more temperate surface, it could have created environments that were at least temporarily favorable for microbial life. Even though the idea of Mercury supporting life may seem improbable, it's important to remember that many of the assumptions we make about habitability are based on Earth-centric perspectives. Life on Earth thrives in extreme environments, deep-sea hydrothermal vents, acidic hot springs, and even beneath Antarctic ice. If life is capable of adapting to such extreme conditions, could similar extremophiles have evolved on Mercury? While this is pure speculation, the discovery of water ice in permanently shadowed craters at Mercury's poles keeps the question open. The permanently shadowed craters, where water ice has been detected, offer some of the most intriguing locations for future exploration. These cold traps have not seen sunlight in billions of years, and the temperatures inside them are some of the coldest in the solar system, dropping to as low as -173 degrees Celsius -279 degrees Fahrenheit. Despite Mercury's close proximity to the Sun, these craters remain incredibly cold because their steep walls block any direct sunlight, creating regions that could preserve ice for immense periods of time. The ice in these craters is likely mixed with other volatile compounds, and studying the composition of these deposits could provide valuable clues about how water arrived on Mercury. Some scientists believe that comets, which are known to contain large amounts of water, could have bombarded Mercury early in its history, delivering water to the planet's surface. Others suggest that water may have been outgassed from Mercury's interior through volcanic activity, or that micrometeoroids regularly bring water to the planet. While the presence of water ice on Mercury is tantalizing, it is still uncertain how thick these ice deposits are and whether they are accessible enough to be of practical use for future exploration. Harvesting ice from these craters could provide a critical resource for future missions, potentially offering a source of water for astronauts, which could be used for drinking, growing food, or even splitting into hydrogen and oxygen for rocket fuel. This would make Mercury a valuable stopover point for missions further into the solar system. Beyond the water ice, the surface of Mercury itself holds many mysteries. The planet's landscape is a mixture of heavily cratered regions and relatively smooth plains, suggesting a complex geological history. The smooth plains are thought to be the result of ancient volcanic activity, which resurfaced large portions of the planet. Some of these plains may be over 3 billion years old, while others could be much younger, indicating that Mercury's volcanic history may have spanned a significant portion of its existence. The discovery of relatively young volcanic features on Mercury is surprising because smaller planets like Mercury are expected to cool and solidify relatively quickly. Yet, evidence from the MESSENGER mission suggests that Mercury may have experienced volcanic activity long after its formation. Some scientists believe that Mercury's large iron core, which makes up about 85% of the planet's radius, may still be generating enough heat to drive volcanic eruptions, although this remains a topic of debate. Mercury's volcanic activity is closely tied to its internal structure, which is one of the planet's most puzzling features. As previously mentioned, Mercury has an unusually large core relative to its size, which raises questions about how the planet formed. One leading hypothesis is that Mercury was once much larger, but a giant impact early in the solar system's history stripped away much of its outer layers, leaving behind the dense, metal-rich planet we see today. If this impact theory is correct, it would mean that Mercury's core is much closer to the surface than Earth's, which could explain some of the planet's unique geological features, such as its scarps and smooth plains. However, this theory also raises questions about Mercury's magnetic field, which is much weaker than Earth's but still surprisingly strong for such a small planet. The generation of a magnetic field is typically driven by the movement of molten iron in a planet's core, and the fact that Mercury still has a magnetic field suggests that its core is at least partially molten. The offset nature of Mercury's magnetic field adds another layer of complexity to this mystery. Unlike Earth's magnetic field, which is centered on the planet's core, Mercury's magnetic field is shifted northward by about 20%. This asymmetry suggests that something unusual is happening in Mercury's interior, possibly related to the way heat is being transferred between the core and the mantle. Understanding why Mercury's magnetic field is offset could provide new insights into how magnetic fields are generated on other planets, including Earth. Mercury's weak and asymmetric magnetic field also creates some interesting interactions with the solar wind. Because Mercury is so close to the Sun, it is constantly bombarded by charged particles from the solar wind, which can have dramatic effects on the planet's magnetosphere. The solar wind can compress Mercury's magnetic field on the Sun-facing side and stretch it out on the opposite side, creating a long magnetic tail. This tail can interact with particles from the solar wind, generating magnetic storms and auroras similar to those seen on Earth, although much weaker. The constant bombardment of the solar wind also has a direct impact on Mercury's surface. Unlike Earth, which has a thick atmosphere to protect it from the solar wind, Mercury's thin exosphere provides little protection. As a result, the solar wind constantly strips away particles from Mercury's surface, a process known as space weathering. This space weathering has a noticeable effect on the planet's surface, darkening the regolith, the loose, dusty material on the surface, and altering its composition over time. Mercury's lack of a substantial atmosphere also makes it vulnerable to extreme temperature swings. During the day, temperatures on the sunlit side of the planet can reach as high as 430 degrees Celsius (800 degrees Fahrenheit), while at night, temperatures can plummet to -180 degrees Celsius (-290 degrees Fahrenheit). These extreme temperature changes create a harsh environment that would be challenging for any future exploration missions. However, Mercury's polar regions, where water ice has been detected, may offer more stable and potentially more hospitable conditions for future exploration. The polar regions are not only home to water ice but also to some of the most mysterious features on Mercury. The permanently shadowed craters at the poles are thought to be some of the coldest places in the solar system, and they may contain ancient deposits of ice and other volatiles that have been preserved for billions of years. Studying these deposits could provide valuable insights into the history of water in the solar system and the processes that shaped Mercury's evolution. Mercury's proximity to the Sun makes it a unique laboratory for studying the effects of solar radiation on a planet's surface and atmosphere. The planet's thin exosphere is constantly being bombarded by solar radiation, which can knock particles off the surface and create a tenuous atmosphere composed of hydrogen, helium, oxygen, sodium, potassium, and other elements. This exosphere is constantly being replenished by particles from the solar wind and by micrometeoroid impacts, which release material from Mercury's surface. One of the most intriguing aspects of Mercury's exosphere is the presence of sodium, which has been observed in high concentrations around the planet's poles. The source of this sodium remains a mystery, but some scientists believe that it may be released from the surface by micrometeoroid impacts or by solar radiation. Understanding the processes that generate and sustain Mercury's exosphere could provide important clues about the planet's interaction with the solar wind and its overall atmospheric dynamics. Mercury's exosphere also provides a unique opportunity to study the interaction between the solar wind and a planet without a significant atmosphere. Unlike Earth, where the atmosphere shields the surface from the solar wind, Mercury's exosphere offers little protection, allowing scientists to observe how the solar wind directly impacts the surface. This makes Mercury an ideal target for studying space weathering and the effects of the solar wind on planetary surfaces. The mysteries of Mercury's exosphere, magnetic field, and geological history make the planet a fascinating subject for future exploration. While the MESSENGER mission provided a wealth of data about Mercury, there is still much we don't know about the planet. For example, we have only limited information about the composition of Mercury's core and mantle, and the processes that drive the planet's tectonic activity remain poorly understood. Future missions to Mercury could help answer some of these questions. The European Space Agency's BepiColombo mission, which launched in 2018, is currently en route to Mercury and is expected to arrive in 2025. BepiColombo will study Mercury's magnetic field, exosphere, surface composition, and internal structure in unprecedented detail, providing new insights into the planet's formation and evolution. Mercury's mysteries extend beyond its exosphere and magnetic field, diving deep into its enigmatic core and surface composition. As one of the least explored planets in the solar system, Mercury poses a series of tantalizing questions that challenge our understanding of planetary formation and evolution. BepiColombo, a joint mission between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, is poised to fill the gaps left by previous missions like MESSENGER. By studying Mercury with advanced instruments and flying closer to its surface, this mission aims to unlock some of the planet's most profound secrets. One of the most intriguing aspects of Mercury that BepiColombo will explore is the structure of its core. Scientists believe that Mercury has the largest core-to-planet ratio in the solar system, which accounts for about 85% of its volume. The exact composition and state of this core remain a mystery, but it is thought to be primarily composed of iron. One theory suggests that this core could be partly molten, which might explain the generation of Mercury's magnetic field, although the precise mechanism remains unclear. BepiColombo will carry a magnetometer to investigate the strength and orientation of Mercury's magnetic field, potentially providing critical data about the dynamics of its core. The idea that Mercury's core might still be molten is surprising, given the planet's small size and the assumption that smaller planets cool and solidify quickly. Mercury's core could be partially liquid due to the planet's unusual internal structure, where heat from radioactive decay could still be driving the dynamo effect responsible for the magnetic field. Understanding the nature of this core could reveal not only details about Mercury's history but also offer broader insights into planetary magnetism, a phenomenon that has puzzled scientists for decades. The peculiarities of Mercury's magnetic field, as mentioned earlier, have long been a subject of fascination. Unlike Earth's magnetic field, which is largely centered on the planet's core, Mercury's field is offset by about 20% to the north. This strange asymmetry creates a unique magnetosphere that interacts with the solar wind in ways that differ significantly from Earth's. The magnetic field plays a key role in shaping Mercury's exosphere, as charged particles from the solar wind are funneled along magnetic field lines to the poles, where they interact with surface material, potentially releasing sodium and other elements into the exosphere. Understanding Mercury's exosphere is critical to grasping how the planet interacts with the solar wind and how its surface has evolved over billions of years. Because Mercury lacks a substantial atmosphere, the solar wind directly impacts the surface, eroding it and contributing to the generation of its thin exosphere. BepiColombo's instruments will measure the composition of the exosphere in greater detail than ever before, revealing how elements like sodium and oxygen are released and how the solar wind affects the planet's surface over time. Another key aspect of Mercury's exploration is its surface features. MESSENGER revealed that Mercury's surface is covered with a mix of impact craters, smooth plains, and towering scarps, indicating a complex geological history. Some of the smooth plains are thought to have been formed by ancient volcanic activity, resurfacing the planet over time. These plains provide clues about Mercury's internal processes, including how its mantle and core have interacted to drive volcanic activity. Some of the plains are ancient, dating back over 3 billion years, but others could be much younger, suggesting that Mercury's geological activity persisted for much longer than previously thought. One of the most striking features on Mercury's surface is the presence of lobate scarps, which are large cliffs formed by the planet's crust shrinking as it cooled. These scarps, some of which rise several kilometers high, are thought to have been created by Mercury's core contracting as it solidified. The scarps suggest that Mercury is still shrinking, a process that may be ongoing even today. Understanding how these features formed and continue to evolve will provide valuable insights into the planet's internal structure and thermal history. Mercury's surface also contains a number of large impact basins, including the enormous Caloris Basin, which is one of the largest impact craters in the solar system. The formation of this basin likely had a profound impact on the planet's geological and tectonic history. The Caloris Basin is surrounded by a series of concentric rings, indicating the immense force of the impact that created it. Studying these impact features can provide clues about the early solar system, including the frequency and size of asteroid collisions that shaped Mercury and other planets. One of the enduring questions about Mercury's surface is the origin of its enigmatic hollows. These shallow, irregular depressions are scattered across the surface and appear to be relatively young, suggesting that they are still actively forming. The exact process that creates these hollows is unknown, but they are thought to be linked to the sublimation of volatile materials from Mercury's crust, possibly due to the intense heat and radiation from the Sun. Understanding how these hollows form could provide new insights into the composition of Mercury's surface and its volatile inventory. Mercury's volatile composition, in particular, is a key area of interest for scientists because it contradicts some of the expectations for a planet so close to the Sun. Volatiles are substances that easily vaporize, and they include elements like hydrogen, helium, and certain metals. Given Mercury's proximity to the Sun, it was expected that these elements would have been stripped away early in the planet's history. However, MESSENGER revealed that Mercury has surprisingly high levels of volatiles, including sulfur and potassium, which are not typically found in large amounts on bodies that formed in such hot conditions. This unexpected volatile content has led to new theories about how Mercury may have formed. Some scientists suggest that Mercury may have formed farther from the Sun, where temperatures were cooler, and later migrated inward to its current position. This migration could have preserved some of the volatile elements that would have been lost if the planet had formed in its current location. Alternatively, the volatiles could have been delivered to Mercury by comets and asteroids that impacted the planet over time, although this would still require an explanation for why so many volatiles survived the intense heat. Another mystery related to Mercury's surface is its unexpectedly dark appearance. Mercury reflects very little sunlight compared to other rocky planets, making it one of the darkest bodies in the solar system. This low reflectivity, or albedo, suggests that the planet's surface is covered with a dark material, but the source of this material remains unclear. Some scientists believe that the darkening could be due to the presence of carbon, possibly in the form of graphite, which may have been deposited on the surface by comets, or released from Mercury's interior during volcanic eruptions. Alternatively, the dark material could be the result of space weathering, as Mercury's surface is constantly bombarded by micrometeoroids and solar wind particles that can darken the regolith over time. Understanding the composition and origin of this dark material is important not only for understanding Mercury's surface but also for gaining insights into the processes that shape planetary surfaces across the solar system. Mercury's dark, volatile-rich surface raises questions about how the planet's atmosphere has evolved over time. While Mercury has only a tenuous exosphere today, it may have had a thicker atmosphere in the past. Early in its history, Mercury was likely more geologically active, with volcanic eruptions releasing gases into the atmosphere. Over time, however, the planet's weak gravity and proximity to the Sun likely caused much of this atmosphere to escape into space. Today, Mercury's exosphere is replenished by the solar wind and micrometeoroid impacts, but it is only a faint shadow of the atmosphere that may have once existed. Despite its thin exosphere, Mercury experiences significant space weathering effects, especially on the day side, where temperatures soar and solar radiation is intense. The extreme environment on Mercury's surface creates unique conditions for studying how planetary bodies interact with their parent stars. By understanding how the solar wind and radiation affect Mercury's surface and exosphere, scientists can gain insights into the processes that shape other planets and moons, particularly those orbiting close to their stars. As we continue to explore Mercury, many of these questions will likely be answered, but new mysteries are sure to arise. Bepicolombo's detailed observations of the planet's magnetic field, exosphere, and surface will provide critical data that could reshape our understanding of Mercury's history and its place in the solar system. Ultimately, Mercury's story is a window into the processes that shape not only our own planet but the entire solar system. The planet's extreme conditions, unusual geology, and unique magnetic environment make it a fascinating subject of study and one that will continue to captivate scientists for years to come. Mercury's status as a planet of extremes continues to raise profound questions about the formation and evolution of rocky planets in our solar system. As the smallest and closest planet to the Sun, Mercury is a natural laboratory for understanding how intense solar radiation and gravitational forces can sculpt a world over billions of years. Despite its proximity to the Sun, Mercury retains key features that contradict what we might expect from a planet so close to a stellar furnace. One of the most surprising discoveries from missions like Messenger and future missions such as Bepicolombo is the detection of water ice in permanently shadowed craters near Mercury's poles. The existence of ice on such a hot planet initially seems paradoxical. However, the extreme tilt of Mercury's rotational axis, which is almost perfectly upright, means that some craters at the poles never receive sunlight. These shadowed regions, known as cold traps, can maintain temperatures far below freezing, even though the rest of the planet experiences extreme heat during its day. Messenger's data provided evidence of bright radar signatures consistent with water ice deposits in these polar craters. Scientists believe that the ice may have been delivered by comets or asteroids that impacted Mercury's surface over time. This ice is likely mixed with other volatile compounds, such as sulfur and carbon dioxide, which could help preserve it in the harsh conditions near the poles. The presence of water ice on Mercury raises intriguing questions about the availability of volatiles in the inner solar system, and how they have been preserved on airless bodies like Mercury and the Moon. The discovery of ice on Mercury adds another layer of complexity to the planet's history and evolution. It suggests that Mercury may have retained some of the building blocks necessary for life, at least in the form of water, despite being one of the most inhospitable planets in the solar system. While the idea of life on Mercury seems improbable, the discovery of water ice opens up new avenues for research into the origins of water in the inner solar system and how planets without atmospheres can preserve volatiles over time. In addition to water ice, Mercury's poles offer other mysteries. The distribution of the ice deposits, for example, is not uniform. Some areas contain more ice than others, and scientists are still working to understand why. It is possible that differences in the age of craters, the amount of sunlight they receive, or the composition of the surface materials could all play a role in determining where ice accumulates. Studying the polar regions of Mercury in more detail could provide clues about how the planet's surface interacts with external sources of volatiles, such as comets, and how the solar wind affects the distribution of these materials over time. Another aspect of Mercury's mystery involves its ancient volcanic activity. The planet's surface contains vast plains that were likely formed by large-scale volcanic eruptions early in its history. Unlike the Earth, where volcanism is often driven by plate tectonics, Mercury's volcanic activity seems to be the result of internal heat released as the planet cooled. As Mercury's core shrank, the pressure on the mantle may have caused magma to rise to the surface, creating smooth plains that filled in impact craters and reshaped the landscape. These volcanic plains provide a snapshot of Mercury's early history, revealing that the planet was once much more geologically active than it is today. Some of the lava flows on Mercury's surface are over 3.5 billion years old, suggesting that volcanism played a major role in shaping the planet during the first billion years of its existence. Understanding the timing and extent of Mercury's volcanic activity is critical for piecing together the planet's geological history and how it compares to other terrestrial planets like Earth, Mars, and Venus. The evidence of volcanic activity on Mercury also raises questions about the planet's internal heat sources. For a small planet like Mercury, we might expect it to have cooled and become geologically inactive relatively quickly. However, The presence of volcanic plains and the planet's ongoing contraction suggests that Mercury retained enough internal heat to drive volcanism for a much longer period than previously thought. This prolonged activity could be linked to the planet's large iron core, which may have acted as a reservoir of heat, slowly releasing energy over billions of years. Mercury's slow cooling is also tied to its continued shrinking, as evidenced by the large lobate scarps that crisscross the surface. These scarps, some of which stretch for hundreds of kilometers, are essentially cliffs formed as the planet's crust buckled under the strain of its contracting interior. Mercury is the only planet in the solar system known to be actively shrinking in this way, and studying these scarps can provide insights into how planetary interiors evolve over time. The process of planetary contraction on Mercury is still ongoing, suggesting that the planet's interior remains dynamic. While Mercury lacks the plate tectonics that drive geological activity on Earth, its shrinking crust still creates tectonic features that record the planet's cooling history. These features offer a window into the final stages of planetary evolution, showing how planets with large metal cores lose heat and how this process shapes their surfaces. In contrast to its shrinking interior, Mercury's surface remains a dynamic environment, constantly shaped by space weathering. The planet is bombarded by micrometeoroids and solar wind particles at a much higher rate than other planets due to its proximity to the Sun. This constant bombardment erodes the surface and can release volatile elements like sodium and potassium, which are then swept up into the exosphere. Over time, these impacts gradually alter the composition of the surface, darkening it and creating a layer of regoliths similar to the surface of the Moon. One of the key questions about Mercury's surface is the role of space weathering in shaping its albedo, or reflectivity. Mercury is one of the darkest planets in the solar system, reflecting only about 6% of the sunlight that strikes it. This low albedo suggests that Mercury's surface is covered with a dark material, but the exact nature of this material is still debated. Some scientists believe that the darkening could be due to the accumulation of carbon from cometary impacts, while others suggest that it could be the result of space weathering processes that have altered the surface minerals over billions of years. Understanding the source of Mercury's dark surface is important for interpreting data from future missions and for understanding how space weathering affects other airless bodies in the solar system. The comparison between Mercury and the Moon, for example, can provide insights into how different factors, such as proximity to the Sun and variations in surface composition, influence the space weathering process. Mercury's unique environment, with its extreme temperatures and high levels of solar radiation, makes it a valuable case study for understanding the effects of space weathering on planetary surfaces. Another intriguing aspect of Mercury's surface is the presence of strange bright spots and halos. These features are unlike anything seen on other planets, and represent one of Mercury's most mysterious surface phenomena. Halos are irregular, shallow depressions that appear to be relatively young, suggesting that they are still actively forming. They are often associated with impact craters and appear to be the result of volatile materials sublimating from the surface, leaving behind a hollowed-out area. The formation of halos is still not fully understood, but they may be linked to the volatile-rich nature of Mercury's surface. The intense heat and solar radiation experienced on the day side of Mercury could cause certain materials to vaporize, particularly in areas where the crust has been fractured by impacts. Over time, this process could create the strange, pitted terrain seen in many of the halos. Colombo will study these features in greater detail, providing data that could help resolve the mystery of how they form and what they reveal about Mercury's surface composition. The exploration of Mercury has opened up new questions about the nature of planetary formation and evolution, particularly for planets in the inner solar system. Despite being the closest planet to the Sun, Mercury has defied expectations in many ways, from its large iron core and magnetic field to its volatile-rich surface and water ice deposits. Each new discovery about Mercury challenges our assumptions about how planets form and evolve in extreme environments. As we continue to study Mercury with missions like Baby Colombo, we will likely uncover even more surprises about this enigmatic planet. The data gathered from these missions will not only shed light on Mercury's unique characteristics but also help us understand the broader processes that shape the solar system. Mercury's extreme environment, from its scorching daytime temperatures to its icy polar regions, provides a valuable opportunity to study the limits of planetary formation and how planets adapt to their surroundings. In many ways, Mercury is a microcosm of the solar system's history, preserving evidence of the processes that shaped not only its own evolution but also the evolution of the other terrestrial planets. From its ancient volcanic plains to its actively shrinking crust, Mercury's story is one of dynamic change and adaptation. By studying this small but complex planet, we can gain insights into the fundamental forces that have shaped our solar system and continue to shape planetary bodies throughout the universe. Mercury, despite being the closest planet to the Sun, remains a scientific enigma. Its harsh environment and the extremes it endures offer a unique window into planetary processes that can occur in such a hostile region of space. From its massive iron core to its thin exosphere and from water ice deposits to hollows on its surface, Mercury continues to defy expectations, challenging scientists to rethink their understanding of planet formation, solar interactions, and space weathering. One of the key features of Mercury that distinguishes it from other planets in our solar system is its magnetic field. The presence of a magnetic field was unexpected because Mercury, due to its small size, should have cooled and become geologically inactive billions of years ago. However, the discovery of a global magnetic field by Mariner 10 in the 1970s and later confirmed by MESSENGER suggests that Mercury's core is still partially molten, allowing it to generate a magnetic dynamo. This magnetic field is about 1% as strong as Earth's, but it is still significant, especially given Mercury's proximity to the Sun. The interaction between Mercury's magnetic field and the solar wind creates what is known as a magnetosphere. Mercury's magnetosphere, though small, acts as a shield that deflects solar wind particles around the planet. However, because Mercury is so close to the Sun, its magnetosphere is constantly bombarded by high-energy particles, leading to dynamic changes. These interactions can strip away particles from Mercury's thin exosphere, contributing to its constantly changing composition. The discovery of Mercury's magnetic field also raises questions about the structure of its core. Based on data from MESSENGER, scientists now believe that Mercury's core makes up a larger fraction of its volume than any other planet in the solar system. The core may account for up to 85% of the planet's radius, with the rest being a relatively thin mantle and crust. This unusual core size may be the result of Mercury forming in a different part of the solar system and migrating inward, or it could be due to early collisions that stripped away much of its original mantle. Another puzzle surrounding Mercury's core is how it remains partially molten despite the planet's small size. One hypothesis is that the core contains lighter elements, such as sulfur, which lower the melting point of the material, allowing the core to remain in a liquid state longer. Alternatively, the tidal forces from the Sun's gravity may play a role in keeping the core partially molten. These forces could cause Mercury's interior to flex and generate heat, much like how tidal forces heat the interior of Jupiter's moon Io. Understanding Mercury's core and magnetic field is not just important for understanding the planet itself but also for understanding planetary magnetism in general. Mercury's magnetic field is weaker than Earth's, and its magnetosphere is much more compressed due to the proximity to the Sun. This creates a unique environment where we can study how magnetic fields and solar wind interactions work in extreme conditions. Future missions like BepiColombo will continue to study Mercury's magnetosphere in greater detail, helping scientists refine their models of how planetary magnetic fields are generated and how they interact with the solar wind. Another fascinating aspect of Mercury is its orbit and rotation. Mercury has an unusual 3:2 spin-orbit resonance, meaning that it rotates 3 times on its axis for every 2 orbits it completes around the Sun. This leads to a day on Mercury, from one sunrise to the next, lasting 176 Earth days, while a single year on Mercury takes only 88 Earth days. This strange rotational pattern results in extreme temperature variations, with surface temperatures reaching over 800 degrees Fahrenheit, 427 degrees Celsius, during the day and plummeting to -290 degrees Fahrenheit, -180 degrees Celsius, at night. These extreme temperature swings pose additional challenges for studying the planet. The daytime side of Mercury experiences scorching heat, while the night side plunges into freezing cold. This makes it difficult for spacecraft to operate, and it also means that any volatile materials, like water or organic compounds, are quickly broken down or evaporated when exposed to sunlight. However, the discovery of water ice in permanently shadowed craters shows that even on Mercury, pockets of material can remain stable for billions of years if they are protected from the sun's heat. Mercury's eccentric orbit is another aspect that has intrigued scientists for centuries. Its orbit is the most elliptical of all the planets, meaning that its distance from the Sun varies significantly over the course of its year. This eccentric orbit was one of the key factors that led to the development of Einstein's theory of general relativity. The precession of Mercury's orbit could not be fully explained by Newtonian mechanics, but Einstein's theory of general relativity accounted for the discrepancy, providing one of the first confirmations of the theory. The fact that Mercury's orbit played a role in the development of such a fundamental scientific theory highlights the planet's importance in the broader context of astrophysics and planetary science. Even though it is the smallest and least massive of the terrestrial planets, Mercury has a disproportionately large impact on our understanding of the solar system and the forces that govern planetary motion. Another area of ongoing research related to Mercury's orbit is its long-term stability. Due to the gravitational interactions between Mercury and the other planets, especially Venus and Jupiter, its orbit is subject to chaotic changes over long periods. Some simulations suggest that Mercury's orbit could become even more eccentric in the distant future, potentially leading to a collision with Venus or even being ejected from the solar system altogether. While these events are unlikely to occur for billions of years, they underscore the complexity of the gravitational interactions that shape the architecture of our solar system. Mercury's surface, too, continues to fascinate scientists. The planet is covered in craters, the result of billions of years of impacts from asteroids and comets. Some of these craters are enormous, with the largest, Caloris Basin, stretching over 1,500 kilometers in diameter. Caloris Basin is one of the largest impact basins in the solar system and is surrounded by a ring of mountains that rise up to 2 kilometers high. The impact that formed Caloris Basin would have released an incredible amount of energy, reshaping Mercury's surface and potentially causing volcanic eruptions on the opposite side of the planet due to the seismic shock. In addition to its heavily cratered surface, Mercury also features long, sinuous scarps, or cliffs, that crisscross the planet. These scarps are the result of Mercury's crust contracting as the planet cooled and its core shrank. Some of these scarps are hundreds of kilometers long and rise several kilometers high, making them some of the most striking geological features on the planet. The discovery of these scarps suggests that Mercury has been cooling and shrinking for billions of years, and the process may still be ongoing today. Mercury's surface also contains areas that appear to be unusually smooth and relatively free of craters. These smooth plains are thought to be the result of ancient volcanic activity, where lava flows filled in craters and created flat, featureless regions. This evidence of volcanism on Mercury suggests that the planet was once much more geologically active than it is today. However, unlike Earth, where plate tectonics drive much of the volcanic activity, Mercury's volcanism seems to have been driven primarily by internal heat and pressure from the planet's shrinking core. Another mysterious feature of Mercury's surface is the presence of hollows. These are shallow, irregular depressions that appear to be relatively young and may still be actively forming. Hollows are often found on the floors of impact craters and are thought to be the result of volatile materials sublimating away, leaving behind a hollowed-out depression. The exact composition of these volatiles is still unknown, but they may include elements like sulfur or carbon compounds. The discovery of hollows adds another layer of complexity to Mercury's surface, suggesting that the planet's surface is still evolving in subtle ways. The exploration of Mercury by spacecraft has provided a wealth of data, but many questions remain unanswered. Future missions, like ESA's BepiColombo, which launched in 2018 and is expected to arrive at Mercury in the late 2020s, will continue to study the planet in greater detail. BepiColombo consists of 2 orbiters, one built by the European Space Agency, ESA, and the other by the Japan Aerospace Exploration Agency, JAXA. Together, these orbiters will map Mercury's surface, study its magnetic field, and analyze its exosphere, building on the discoveries made by Mariner 10 and Messenger. Bepi-Colombo's dual orbiter design allows for a more comprehensive study of Mercury's magnetic field and exosphere. By studying the interactions between Mercury's magnetosphere and the solar wind, scientists hope to gain a better understanding of how magnetic fields operate in extreme environments. Bepi-Colombo will also provide high-resolution images of Mercury's surface, helping to identify new geological features and further investigate the planet's volcanic history, hollows, and tectonic activity. Mercury may be the smallest planet in our solar system, but it is far from insignificant. Its extreme environment, dynamic surface, and mysterious interior make it a key target for understanding planetary evolution and the forces that shape rocky planets. The discoveries made by past missions like Messenger, and the data expected from future missions like Bepi-Colombo will continue to unravel the many mysteries of Mercury, offering new insights into the history and future of our solar system. The mysteries of Mercury extend beyond its internal composition, magnetic field, and surface features. One of the most surprising discoveries on Mercury is the existence of water ice in its polar regions. Despite being the closest planet to the Sun, Mercury has permanently shadowed craters near its poles where sunlight never reaches. These regions, which remain in eternal darkness, are cold enough to harbor frozen water, and this discovery has profound implications for our understanding of the planet. The presence of water ice on Mercury was first suggested in the 1990s when radar observations from Earth detected highly reflective patches at the planet's poles. These radar-bright regions were consistent with the signature of water ice, but direct confirmation had to wait until the Messenger mission. When Messenger arrived at Mercury in 2011, it used neutron spectrometry to measure the hydrogen content of the planet's surface. The results confirmed that there were significant amounts of hydrogen in the radar-bright regions, indicating the presence of water ice. The discovery of water ice on Mercury raises several important questions. How did the water get there? How has it remained stable over billions of years in such a harsh environment? And what does this tell us about the potential for water on other celestial bodies in our solar system? One possible source of Mercury's water ice is comets and asteroids. These objects, which frequently collide with planets, are known to contain large amounts of water. Over billions of years, cometary impacts could have delivered water to Mercury, some of which became trapped in the permanently shadowed craters at the poles. Another possibility is that Mercury's water could have originated from volcanic activity early in the planet's history. Water vapor released by volcanic eruptions might have migrated to the poles, where it condensed and froze. Regardless of its origin, the fact that water ice can survive on Mercury suggests that other seemingly inhospitable worlds might also harbor hidden reservoirs of water. The presence of water ice on Mercury adds to a growing list of places in the solar system where water exists, including the Moon, Mars, Europa, and Enceladus. This broad distribution of water increases the likelihood that other planets and moons might have the necessary conditions to support life, at least in some form. In addition to water ice, Mercury's polar regions may also contain other volatile materials. Messenger's data suggests that alongside the water ice, there may be deposits of other frozen substances, such as sulfur or carbon dioxide. These volatiles could provide clues about the planet's history and the processes that have shaped its surface over time. Understanding the composition and distribution of these materials is a key goal of future missions like Bepi-Colombo. The discovery of water ice on Mercury has also fueled speculation about the planet's potential as a resource for future human exploration. Although Mercury's environment is incredibly hostile, with extreme temperatures and high levels of radiation, the water ice in its polar regions could be used as a resource by future missions. Water could be harvested for drinking, converted into oxygen for breathing, or even used to produce hydrogen fuel for rockets. In this way, Mercury could play a role in future missions to the inner solar system, serving as a refueling station for spacecraft traveling to and from Venus or the Sun. However, any human mission to Mercury would face enormous challenges. The intense heat on the planet's sunlit side combined with the freezing cold on its night side would require spacecraft and habitats to have advanced thermal protection systems. The high levels of solar radiation would also pose a significant risk to astronauts, requiring the use of radiation shielding and other protective technologies. Additionally, Mercury's low gravity, only 38% of Earth's, could lead to long-term health effects for humans, similar to the challenges posed by prolonged stays on the Moon or Mars. Despite these challenges, the discovery of water ice on Mercury shows that even the most extreme environments in our solar system can still surprise us with their potential for exploration and resource utilization. It also underscores the importance of continuing to explore the solar system, as each new discovery adds to our understanding of the planets and moons that make up our cosmic neighborhood. Another fascinating aspect of Mercury that scientists are still trying to understand is its exosphere. Unlike Earth, which has a thick atmosphere, Mercury has an exosphere, a tenuous layer of atoms and molecules that are so sparse that they rarely collide with one another. Mercury's exosphere is composed primarily of hydrogen, helium, oxygen, sodium, potassium, and calcium, but it is constantly being replenished as atoms are ejected from the surface or captured from the solar wind. The exosphere is so thin that it is practically a vacuum, but it is still an important part of the planet's environment. The atoms and molecules in Mercury's exosphere come from a variety of sources. Some are the result of solar wind particles striking the surface and knocking atoms into space. Others come from micrometeoroid impacts that vaporize surface material, releasing atoms into the exosphere. Some of the exosphere's constituents, such as sodium and potassium, may also be the result of chemical reactions in Mercury's surface rocks. Because Mercury's exosphere is constantly being stripped away by the solar wind, it must be continually replenished. This delicate balance between loss and replenishment creates a dynamic and ever-changing exosphere. Scientists study the exosphere to learn more about the processes that shape Mercury's surface and its interactions with the solar wind. Understanding these processes is also important for understanding how exospheres form and evolve on other planets and moons. One of the most intriguing phenomena observed in Mercury's exosphere is the presence of sodium tails that stream away from the planet. These tails are created when solar radiation exerts pressure on sodium atoms, pushing them away from the planet in long, glowing trails. These sodium tails can stretch for thousands of kilometers into space and are visible using ground-based telescopes. The formation and behavior of these tails provide insights into the complex interactions between Mercury, its exosphere, and the solar wind. The study of Mercury's exosphere is still in its early stages, but it is already revealing new insights into how planets without substantial atmospheres interact with their space environment. These interactions are important for understanding not just Mercury, but also other airless bodies in the solar system, such as the Moon and asteroids. As scientists continue to study Mercury's exosphere, they hope to gain a deeper understanding of the processes that govern planetary atmospheres and space weathering. One of the more recent discoveries about Mercury involves its hollows, strange, shallow depressions scattered across the planet's surface. These hollows were first identified by Messenger, and they are unlike any other features seen on other planets. Hollows are typically found on the floors of impact craters, and they appear to be relatively young, suggesting that they are still forming today. The origin of these hollows remains a mystery, but scientists believe they may be the result of volatile materials sublimating away, leaving behind empty depressions. The discovery of hollows adds another layer of complexity to Mercury's surface geology. If volatiles are indeed responsible for their formation, it suggests that Mercury's surface contains more volatile materials than previously thought. These volatiles could include elements like sulfur or compounds like carbon dioxide, which would sublimate at relatively low temperatures. The presence of volatiles on Mercury is surprising given its proximity to the Sun, where most volatile materials would be expected to evaporate quickly. Hollows may also provide clues about Mercury's past. If they are the result of volatiles sublimating from the surface, it suggests that Mercury may have once had a thicker atmosphere or more active volcanic processes that deposited these materials. Studying hollows could help scientists reconstruct Mercury's geological history and understand how the planet has evolved over time. In addition to hollows, Mercury's surface also contains evidence of ancient volcanic activity. Smooth plains cover large portions of the planet, and many of these plains appear to be the result of ancient lava flows. These volcanic plains suggest that Mercury was once much more geologically active than it is today, with widespread volcanic eruptions reshaping its surface. Volcanism on Mercury likely played a key role in the planet's early evolution. The large impact that created the Caloris Basin, for example, may have triggered volcanic eruptions on the opposite side of the planet, creating a region known as the Weird Terrain. This region is characterized by a chaotic, jumbled landscape, and it is thought to have formed as a result of seismic waves from the Caloris impact converging on the far side of the planet. Understanding Mercury's volcanic history is important for understanding the planet's overall evolution. Volcanic activity would have released gases into the atmosphere, contributing to the formation of Mercury's exosphere. It also played a role in reshaping the planet's surface, filling in craters and creating vast smooth plains. The volcanic history of Mercury is still not fully understood, but future missions may provide more insights into the processes that shape the planet's surface. Mercury's geological features, including its hollows, scarps, and volcanic plains, continue to offer new challenges and opportunities for scientific exploration. Each new discovery adds to the complexity of Mercury's history and deepens our understanding of the processes that have shaped the planet over billions of years. The mysteries of Mercury's surface are closely intertwined with the planet's extreme environment and unique geological features. One of the more dramatic surface features of Mercury is its system of lobate scarps, cliffs that extend for hundreds of kilometers across the planet's surface. These scarps are thought to be the result of Mercury shrinking as its core cooled over time. As the core contracted, the planet's crust crumpled, forming the towering cliffs we see today. These scarps are some of the clearest evidence that Mercury's interior has cooled significantly since its formation. The presence of lobate scarps indicates that Mercury is tectonically active, albeit in a different way than Earth. While Earth's tectonic activity is driven by the movement of large plates, Mercury's tectonic activity is the result of global contraction. The entire planet is shrinking as it loses heat, and this process is still ongoing today. Some of the scarps are relatively young, suggesting that the planet is still tectonically active, with the crust continuing to crumple and deform. This ongoing tectonic activity makes Mercury a fascinating place to study planetary evolution. Most planets in the solar system, including Earth, have experienced some form of tectonic activity in their past, but Mercury's tectonics are unique because they are driven by global contraction rather than the movement of plates. Understanding how this process works on Mercury could provide new insights into the thermal evolution of rocky planets in general, including Earth. Mercury's scarps are also important for understanding the planet's seismic activity. While we don't have seismometers on Mercury to directly measure earthquakes, or Mercury quakes, scientists believe that the planet experiences seismic activity as a result of its shrinking crust. These quakes are likely small compared to the earthquakes we experience on Earth, but they could still play a role in reshaping the planet's surface. Future missions to Mercury could include seismometers to study this activity and provide a more detailed picture of the planet's tectonics. In addition to its geological features, Mercury's extreme environment poses unique challenges and opportunities for exploration. Because Mercury is so close to the Sun, temperatures on its surface can reach over 800 degrees Fahrenheit, 430 degrees Celsius, during the day, but plummet to -290 degrees Fahrenheit, -180 degrees Celsius, at night. This extreme temperature difference is a result of Mercury's thin atmosphere, which provides little insulation. The lack of an insulating atmosphere also means that there is no weather or erosion on Mercury, so surface features remain largely unchanged for billions of years. The extreme temperatures on Mercury create challenges for spacecraft that visit the planet. Any mission to Mercury must be equipped with advanced thermal protection systems to withstand the intense heat from the Sun. Messenger, for example, was equipped with a sunshade to protect its instruments from the Sun's heat. Future missions, such as the European Space Agency's Bepicolombo, will also need to be designed to operate in Mercury's harsh environment. Despite these challenges, Mercury's environment also offers opportunities for scientific discovery. The lack of an atmosphere means that Mercury's surface is exposed to the full force of the solar wind, a stream of charged particles emitted by the Sun. This constant bombardment of particles provides a unique opportunity to study the interactions between a planet's surface and the solar wind. Understanding these interactions is important for understanding space weather and its effects on other planets, including Earth. One of the most intriguing aspects of Mercury's relationship with the Sun is its unusual orbit. Mercury has the most eccentric orbit of any planet in the solar system, meaning that its distance from the Sun varies significantly over the course of its year. At its closest point, called perihelion, Mercury is only about 46 million kilometers, 29 million miles, from the Sun. At its farthest point, called aphelion, Mercury is about 70 million kilometers, 43 million miles, away. This elliptical orbit leads to some strange phenomena on the planet's surface. Because of Mercury's eccentric orbit and its slow rotation, one day on Mercury lasts about 59 Earth days. The Sun appears to move in strange ways in the Mercurian sky. In some regions, the Sun will rise, then briefly set, before rising again. Similarly, at certain times of the year, the Sun will appear to slow down, stop, and then reverse direction in the sky before continuing on its path. These unusual solar movements are the result of Mercury's complex interplay between its rotation and its elliptical orbit. Mercury's orbit is also subject to a phenomenon known as perihelion precession. This means that the point of Mercury's closest approach to the Sun shifts slightly with each orbit, gradually moving around the Sun over time. This precession was one of the key observations that helped confirm Einstein's theory of general relativity. According to general relativity, the presence of massive objects like the Sun warps the fabric of spacetime, causing the orbits of nearby objects to shift. Mercury's perihelion precession matched the predictions made by Einstein's theory, providing some of the first experimental evidence for the theory. The confirmation of general relativity through observations of Mercury's orbit is just one example of how the study of Mercury has contributed to our understanding of fundamental physics. Mercury may be a small planet, but its unique environment and behavior provide valuable opportunities for testing theories of gravity, planetary science, and solar interactions. In addition to its role in testing theories of general relativity, Mercury also provides insights into the formation and evolution of the solar system. As the innermost planet, Mercury formed in a region of the solar system where temperatures were extremely high during the early stages of planetary formation. This extreme environment likely played a key role in shaping the planet's composition, with lighter elements being stripped away by the intense heat and solar radiation, leaving behind a dense, metal-rich planet. Mercury's high density suggests that it has an unusually large iron core for its size. In fact, Mercury's core is believed to make up about 85% of the planet's radius, compared to only about 55% for Earth. This large core, combined with the planet's thin mantle and crust, has led scientists to propose several theories about Mercury's formation. One possibility is that Mercury originally formed as a much larger planet, but its outer layers were stripped away by a giant impact early in its history. Another possibility is that the intense heat and solar radiation in the inner solar system caused the planet's lighter elements to vaporize, leaving behind the dense core. Understanding Mercury's formation is important for understanding the processes that shape the entire solar system. By studying Mercury's composition and structure, scientists can learn more about how planets form and evolve in different regions of a solar system. This knowledge can also be applied to the study of exoplanets, planets orbiting other stars, which may have formed under similar conditions. The study of Mercury continues to reveal new mysteries and challenges our understanding of the solar system. As new missions like Bepi-Colombo prepare to explore the planet in greater detail, we can expect even more surprises from this enigmatic world. From its unusual orbit and magnetic field to its water ice deposits and tectonic activity, Mercury is a planet full of contradictions and surprises. Despite its small size and extreme environment, Mercury plays a crucial role in our understanding of planetary science, space weather, and the early history of the solar system. As we look ahead to future missions and discoveries, Mercury remains a reminder that even the smallest planets can hold some of the greatest mysteries. The more we learn about Mercury, the more we realize how much we still don't know about the planet closest to the Sun. With each new mission, we come one step closer to unraveling the secrets of this ancient world and understanding its place in the grand scheme of the solar system. Mercury's mysteries extend beyond its orbit and surface features, drawing scientists deeper into questions about the planet's internal structure, its origins, and the processes that shaped its evolution. One of the most puzzling aspects of Mercury is its disproportionately large core, which takes up around 85% of its radius. In comparison, Earth's core accounts for only about 55% of its radius, which makes Mercury's internal composition stand out among the rocky planets in the solar system. This unusual structure has led to multiple hypotheses regarding the planet's formation. One of the leading theories about Mercury's large core suggests that the planet may have undergone a catastrophic collision early in its history. In this scenario, a massive impact with another protoplanet or asteroid stripped away much of Mercury's original outer layers, leaving behind the dense, iron-rich core. This would explain why Mercury is so metal-heavy compared to other planets like Earth, Venus, and Mars. Evidence supporting this theory comes from the planet's thin crust and mantle, which seem to be too small for a planet of its size unless something drastic happened during its formation. An alternative hypothesis posits that Mercury's proximity to the Sun played a crucial role in shaping its composition. During the early stages of the solar system's formation, the intense heat and solar wind in the inner regions may have vaporized much of the lighter materials, like silicates, from Mercury's surface, leaving behind the heavier, metallic elements. This process, known as volatile depletion, would have stripped away Mercury's lighter crust and mantle, leaving behind the dense, metal-rich planet we see today. Understanding the nature of Mercury's core is not just a question of planetary composition, it also has important implications for the planet's magnetic field. Mercury is the only rocky planet besides Earth that has a global magnetic field, though Mercury's magnetic field is much weaker than Earth's. Despite its weakness, this magnetic field is a key piece of evidence in unraveling the mysteries of the planet's core. Mercury's magnetic field is thought to be generated by the movement of molten iron within its outer core, a process known as the dynamo effect. This is similar to the mechanism that generates Earth's magnetic field. However, because Mercury's magnetic field is much weaker, it raises questions about how the dynamo process works on a planet with such a small outer core. Some scientists speculate that the planet's core may be cooling and solidifying more quickly than expected, which could be weakening its magnetic field over time. Another mystery surrounding Mercury's magnetic field is its unusual asymmetry. Messenger's observations revealed that Mercury's magnetic field is significantly stronger in the northern hemisphere than in the southern hemisphere. This asymmetry is unlike anything seen on Earth or other planets and suggests that something unusual is happening deep within Mercury's core. Scientists are still trying to understand the cause of this magnetic anomaly, and future missions may provide more insights into this phenomenon. Mercury's magnetic field also plays a role in shaping the planet's interaction with the solar wind. Because Mercury is so close to the Sun, it is constantly bombarded by charged particles from the solar wind. Mercury's magnetic field acts as a shield, deflecting some of these particles, but the planet's weak magnetic field allows many of the particles to reach the surface. This bombardment can strip away particles from the planet's thin exosphere and create dynamic interactions between the surface and the solar wind. The solar wind also interacts with Mercury's magnetic field to create intense magnetic storms, similar to the auroras we see on Earth. However, because Mercury lacks a thick atmosphere, these storms manifest differently. Instead of creating visible light displays like Earth's northern and southern lights, Mercury's magnetic storms result in the direct deposition of solar particles onto the surface, which could have important implications for the planet's geology and surface chemistry. Mercury's surface itself is an interesting blend of ancient craters, smooth plains, and volcanic features. The planet's surface is dominated by impact craters, some of which date back billions of years. Because Mercury lacks weather, tectonic activity, or significant erosion, many of these craters remain well preserved, providing a window into the early history of the solar system. These craters range in size from small, bowl-shaped depressions to massive impact basins, such as the Caloris Basin, which is one of the largest impact structures in the solar system. The Caloris Basin, with a diameter of about 1,550 kilometers, 960 miles, is an especially intriguing feature. It was formed by a massive impact early in Mercury's history, and the force of the collision was so great that it caused weird terrain on the opposite side of the planet, with fractured, jumbled landscapes. The impact also triggered volcanic activity that filled part of the basin with smooth plains, indicating that Mercury was once volcanically active. The volcanic plains on Mercury suggest that the planet experienced widespread volcanic eruptions early in its history. These eruptions helped resurface large areas of the planet, and may have played a role in shaping its current landscape. Some of the volcanic features on Mercury include shield volcanoes and lava channels, which resemble those found on the Moon and Mars. However, Mercury's volcanic activity appears to have ceased long ago, as there is little evidence of recent volcanic eruptions. In addition to its ancient craters and volcanic plains, Mercury's surface is marked by strange, hollowed-out features known as hollows. These bright, shallow depressions are scattered across the planet's surface and are thought to form when volatile materials near the surface sublimate, or turn directly from a solid into a gas, leaving behind pits or hollows. The exact nature of the volatile materials responsible for the hollows is still a mystery, but they may include substances like sulfur or other elements that are easily vaporized by the sun's heat. Mercury's hollows are particularly intriguing because they appear to be relatively young, suggesting that the planet's surface is still evolving in some way. This is surprising for a planet that is otherwise considered geologically dead. The discovery of these features has led scientists to reconsider their understanding of Mercury's geologic activity and to question whether the planet may still be undergoing changes beneath its surface. The mysteries of Mercury extend even to its poles, where scientists have found evidence of water ice in permanently shadowed craters. Despite the planet's proximity to the Sun, these regions never receive direct sunlight, allowing water ice to accumulate and remain stable. The presence of water ice on Mercury was first suggested by radar observations in the 1990s and later confirmed by MESSENGER. The discovery of water ice on Mercury raises important questions about the planet's history and its potential to harbor resources for future exploration. The water ice at Mercury's poles likely came from comets or other icy bodies that impacted the planet, delivering water in the form of ice or vapor. Over time, this water may have migrated to the poles, where it became trapped in the cold, shadowed craters. The presence of water ice on Mercury is surprising given the planet's extreme temperatures, but it shows that even the closest planet to the Sun can retain volatile materials under the right conditions. The discovery of water ice on Mercury has implications for future missions and human exploration. If humans were ever to visit Mercury, the ice at the poles could be a valuable resource for life support and fuel production. However, the extreme environment of Mercury poses significant challenges for human exploration, and much more research is needed before such missions could be considered. Mercury's unique position as the closest planet to the Sun also provides opportunities to study the Sun's influence on planetary bodies. Because Mercury is so close to the Sun, it experiences more intense solar radiation and space weather than any other planet. Studying how Mercury interacts with the Sun can help scientists understand the effects of space weather on other planets, including Earth, and improve our understanding of the Sun's behavior. The mysteries of Mercury continue to captivate scientists and challenge our understanding of the solar system. From its oversized core and unusual magnetic field to its ancient craters and water ice deposits, Mercury is a planet full of surprises. As future missions like BepiColombo explore Mercury in greater detail, we can expect to learn even more about this enigmatic world and its role in the broader context of planetary science. Despite being the smallest planet in the solar system, Mercury plays an outsized role in helping us understand the processes that shape rocky planets. Its unique characteristics offer a window into the early history of the solar system and the forces that continue to shape planetary bodies. The more we study Mercury, the more we realize that this tiny planet has much to teach us about the nature of planetary evolution, space weather, and the formation of the solar system. As researchers delve deeper into Mercury's secrets, one area of intense focus has been its geological history. Mercury's surface is not only characterized by its craters and hollows, but also by its extensive system of cliffs and scarps. These features, some reaching heights of up to 3 kilometers, about 2 miles, suggest that the planet has undergone significant contraction over its history. The formation of these cliffs is thought to be a result of the cooling and shrinking of Mercury's interior as it lost heat over billions of years. This phenomenon of contraction raises intriguing questions about the thermal evolution of Mercury. Unlike Earth, which is tectonically active with shifting plates, Mercury's tectonic activity seems to have ceased long ago. However, the presence of these scarps indicates that there was once enough geological activity to create significant stress in the planet's crust. This could imply that Mercury underwent a period of cooling and contraction after its initial formation, leading to the cracking and folding of its surface. Mercury's extreme temperature variations also contribute to its unique geological processes. Temperatures on the planet can soar to about 430 degrees Celsius, 800 degrees Fahrenheit, during the day, while plunging to around -180 degrees Celsius, -290 degrees Fahrenheit, at night. This drastic temperature swing can cause materials on the surface to expand and contract, leading to cracking and erosion. Such processes might not be sufficient to generate a tectonically active landscape but could contribute to the erosion of surface features over time. Another aspect of Mercury's geology that has captivated scientists is the evidence of past volcanic activity. Messenger's data revealed that the planet's surface contains vast plains formed by ancient volcanic flows. These smooth regions are reminiscent of lunar Maria and indicate that Mercury experienced a significant amount of volcanic activity early in its history. The presence of volcanic vents and unique structures called hollows suggests that volcanic processes may have continued longer than previously thought, extending into more recent geological history. The relationship between volcanic activity and Mercury's core is also a key area of study. The planet's core, which is primarily composed of iron, may still be partially molten. If this is the case, it could lead to volcanic eruptions fueled by the heat from the core. This ongoing thermal activity might explain why some areas of the surface appear to be geologically young, with fewer impact craters than older regions. Understanding this dynamic between Mercury's core and surface will provide insights into the thermal evolution of not only Mercury but also other terrestrial planets. Moreover, Mercury's unique orbital characteristics contribute to its enigmatic nature. The planet has an elliptical orbit that takes it as close as 46 million kilometers, about 29 million miles, to the Sun and as far as 70 million kilometers, about 43 million miles, away. This eccentric orbit influences Mercury's surface temperatures and contributes to the extreme conditions observed on the planet. As it moves closer to the Sun, solar radiation bombards the surface, causing dramatic temperature increases and influencing the planet's geology and exosphere. In addition to its surface features, Mercury's exosphere, the thin atmosphere surrounding the planet, is another area of intrigue. Unlike Earth's thick atmosphere, Mercury's exosphere is tenuous and composed mainly of oxygen, sodium, hydrogen, helium, and potassium. The exosphere is constantly being replenished by solar-wind interactions and the sublimation of surface materials. This delicate balance between incoming solar particles and the planet's surface chemistry results in a dynamic exosphere that changes rapidly over time. Mercury's exosphere has been shown to exhibit significant variations due to solar activity. During periods of heightened solar wind, the exosphere expands and contracts as more particles are pushed towards the surface. This variability raises questions about the long-term stability of Mercury's atmosphere and how it interacts with solar radiation. Future observations will help clarify how these processes influence the composition and dynamics of Mercury's exosphere. Another compelling aspect of Mercury's story is its potential for future exploration. The European Space Agency and Japan Aerospace Exploration Agency's Bepi-Colombo mission, launched in 2018, aims to further investigate the planet's mysteries. Scheduled to arrive in 2025, BepiColombo consists of 2 spacecraft, one for orbiting and another for conducting detailed analyses of the surface and magnetic field. This mission will complement previous observations from MESSENGER and is expected to provide critical data regarding Mercury's composition, geology, and magnetic field. The BepiColombo mission is particularly exciting because it will utilize advanced technology to study Mercury's surface and atmosphere in greater detail than ever before. The mission will investigate the composition of surface materials, analyze the planet's geological features, and study the interactions between the solar wind and Mercury's magnetic field. Such comprehensive research will deepen our understanding of not only Mercury but also the broader processes that govern the evolution of terrestrial planets. The study of Mercury has far-reaching implications for planetary science. By unraveling the mysteries of this small but significant planet, scientists can glean insights into the formation and evolution of rocky planets throughout the solar system. Mercury serves as a key reference point for understanding the processes that shape terrestrial bodies and offers a unique perspective on the history of the solar system. As we look toward the future, the mysteries of Mercury continue to challenge our understanding of planetary science. The planet's unique features, its large core, unusual magnetic field, and dynamic surface, invite exploration and inquiry. The findings from future missions like BepiColombo will undoubtedly enrich our knowledge of Mercury and contribute to a more comprehensive understanding of the complex interplay of forces that govern the evolution of planets in our solar system. Furthermore, the lessons learned from Mercury's geology, atmosphere, and magnetic field can provide valuable context for understanding exoplanets, planets beyond our solar system. As astronomers discover more about these distant worlds, the comparative analysis of Mercury's features and processes may offer clues about the diversity of planetary systems and the conditions that foster planetary development. Mercury stands as a testament to the complexities and mysteries of our solar system. Its unique characteristics challenge our perceptions of planetary formation and evolution, prompting us to reconsider established theories. From its oversized core and active geology to its tenuous atmosphere and dynamic interactions with the Sun, Mercury offers a wealth of information waiting to be uncovered. As we continue to explore this enigmatic world, we can expect to unveil even more secrets that may reshape our understanding of the universe and our place within it. The study of Mercury is a reminder of the importance of exploration and the value of curiosity in expanding our knowledge. Each discovery made on this small planet adds to the rich tapestry of scientific understanding and inspires future generations of scientists to look beyond the familiar and venture into the unknown. Mercury's mysteries may be challenging, but they are also a source of inspiration, driving us to push the boundaries of exploration and deepen our understanding of the cosmos. The enduring allure of Mercury lies in its capacity to provoke questions and ignite our imagination. As we continue to unravel its secrets, we not only learn about this planet but also about the very nature of our solar system and the fundamental processes that govern planetary bodies. The pursuit of knowledge, whether it be through exploration, observation, or theory, remains a cornerstone of human endeavor. As we peer into the depths of space and seek to understand Mercury, we reflect our innate desire to explore, learn, and expand our horizons. Ultimately, the journey to understand Mercury is just beginning. With new missions on the horizon and advancements in technology, the mysteries of this intriguing planet will continue to unfold. Each revelation will contribute to a greater understanding of the forces at play in the universe, reminding us of the vastness of what we have yet to discover. Mercury may be a small planet, but its contributions to our knowledge of planetary science are immense, and its mysteries will continue to inspire exploration and inquiry for years to come. The exploration of Mercury not only enhances our understanding of its unique features but also sheds light on fundamental questions regarding the nature of rocky planets across the universe. As scientists piece together the geological history of Mercury, they consider how its development might mirror or differ from other planets, both within our solar system and beyond. This comparative planetology approach allows researchers to build comprehensive models of planetary evolution that can apply to other celestial bodies. One of the critical insights from studying Mercury is the role of solar radiation and its impact on planetary atmospheres. Mercury's exosphere, characterized by its thin and dynamic nature, serves as a valuable laboratory for understanding how solar winds and radiation can shape planetary atmospheres over time. In contrast to Earth's thick atmosphere, which provides protection from solar and cosmic radiation, Mercury's lack of a substantial atmosphere exposes its surface to direct solar bombardment. This vulnerability leads to ongoing erosion and reformation of surface materials, providing a unique perspective on how atmospheres evolve under varying conditions. Mercury's unusual day-night cycle is another point of interest. The planet has a unique rotation-resonance phenomenon, taking approximately 59 Earth days to complete one rotation on its axis while simultaneously taking about 88 Earth days to orbit the Sun. This results in a peculiar day-night cycle where a single day on Mercury, from one sunrise to the next, lasts about 176 Earth days. This extraordinary configuration influences temperature distribution, with one hemisphere experiencing prolonged daylight, while the other remains in darkness for extended periods. Understanding these dynamics can deepen our knowledge of how other celestial bodies with similar rotational characteristics might behave. The scientific inquiry into Mercury is further enhanced by examining its magnetic field. Mercury possesses a magnetic field that is about 1% the strength of Earth's, yet it remains a subject of fascination due to its complexity. Researchers are investigating how the planet's core dynamics, combined with its swift rotation, contribute to the generation of its magnetic field. The magnetic field's peculiar properties may reveal insights into the core's composition and the planet's thermal history, providing a more nuanced understanding of how smaller, rocky planets develop magnetism. In addition to these physical characteristics, the question of water ice on Mercury has emerged as a tantalizing mystery. Despite its proximity to the Sun, evidence suggests that water ice exists in permanently shadowed craters near the poles, where temperatures remain extremely low. These cold traps could harbor significant deposits of ice, preserved from the Sun's heat due to the unique geometry of the craters. The presence of water ice raises questions about the potential for past or present volatile processes on Mercury, and the implications for understanding the availability of water in the broader solar system. The significance of water on Mercury cannot be understated. It serves as a vital resource in the quest for understanding life beyond Earth. The discovery of water ice in such extreme conditions challenges our assumptions about the requirements for habitability, and opens new avenues for research into the potential for life in environments previously deemed inhospitable. This line of inquiry echoes the search for water on Mars and the icy moons of Jupiter and Saturn, emphasizing the interconnectedness of planetary science and astrobiology. As we look ahead, advancements in technology and instrumentation are poised to revolutionize our understanding of Mercury. Future missions, including the Bepi-Colombo mission, aim to utilize cutting-edge sensors and scientific instruments to probe the planet's surface and atmosphere in unprecedented detail. This includes high-resolution imaging, spectrometry, and advanced magnetic field mapping, enabling scientists to gather comprehensive data that will illuminate the planet's past and present. Moreover, interdisciplinary collaboration among scientists from various fields, geology, astrophysics, atmospheric science, and astrobiology, will play a crucial role in the ongoing exploration of Mercury. The complexities of planetary systems demand a holistic approach, integrating knowledge from multiple domains to form a complete picture of how planets evolve. This collaborative spirit fosters innovation and opens new avenues of inquiry, paving the way for discoveries that could reshape our understanding of the cosmos. In addition to scientific advancements, public interest in Mercury continues to grow. As more people become aware of the intricacies of our solar system, there is a rising curiosity about Mercury and its role within it. Educational initiatives and outreach programs aimed at engaging the public with planetary science foster a deeper appreciation for the mysteries of space. Inspiring the next generation of scientists and explorers is essential for ensuring that our quest for knowledge continues. The allure of Mercury is also reflected in popular culture, where its mysteries have sparked imagination and curiosity. From literature to film, the planet's enigmatic nature has captivated artists and storytellers alike, serving as a canvas for exploring themes of exploration, isolation, and the unknown. These narratives not only entertain but also educate, providing a bridge between scientific discovery and cultural expression. As our understanding of Mercury expands, so too does our appreciation for the intricate processes that shape planetary bodies. The interplay between internal dynamics, external forces, and geological history is a complex dance that reveals the rich tapestry of our solar system. Each revelation about Mercury contributes to a broader understanding of how planets form, evolve, and interact with their environments. In this ever-evolving field of planetary science, Mercury stands out as a beacon of mystery and discovery. It serves as a reminder of the wonders that await beyond our blue planet, encouraging us to explore the unknown and push the boundaries of human knowledge. As we continue to unlock the secrets of Mercury, we not only gain insights into this intriguing world but also embark on a journey that deepens our connection to the cosmos. The continued exploration of Mercury not only holds promise for advancing our scientific understanding but also for inspiring future generations of explorers. The quest for knowledge is a deeply human endeavor, driven by curiosity and the desire to unravel the mysteries that surround us. As we gaze at the night sky and ponder the nature of our universe, we are reminded of our place within it, a small but significant part of a vast and intricate cosmos. As we move forward, the study of Mercury and its mysteries will remain a focal point of planetary science. The ongoing research and upcoming missions will undoubtedly yield new insights and discoveries, enriching our understanding of not just Mercury but also the broader processes that govern the evolution of rocky planets. The excitement of unveiling these secrets propels us into the future, fostering a spirit of exploration that transcends boundaries and unites us in our quest for knowledge. Mercury, with its unique attributes and intriguing history, serves as a powerful symbol of the mysteries that the universe holds. Its extreme environment, geological features, and potential for water ice invite exploration and inquiry, challenging our understanding of planetary systems. As we continue to unlock the secrets of Mercury, we are reminded of the importance of curiosity, collaboration, and exploration in our quest to understand the cosmos. The journey is far from over, and the mysteries of Mercury await the next generation of explorers eager to unveil their secrets. As our exploration of Mercury unfolds, the insights we gain resonate far beyond the planet itself, touching on broader themes that govern planetary science and our understanding of the universe. Each piece of data collected, every image captured, adds to a narrative that not only enriches our knowledge of Mercury but also enhances our understanding of terrestrial planets, their formation, and their evolution over billions of years. A particularly compelling aspect of Mercury is its geology. Scientists have identified a variety of geological features that offer clues about the planet's past. The surface of Mercury is marked by large impact craters, smooth plains, and rugged highlands, all of which tell a story of violent cosmic history. The Caloris Basin, one of the largest impact basins in the solar system, is a focal point for geological studies. Formed by a massive collision early in the planet's history, the Caloris Basin is about 1,550 kilometers, approximately 963 miles, wide and is surrounded by a ring of mountains. The basin's unique characteristics and the geological processes that shaped it are subjects of active research, providing a window into Mercury's violent past and the forces that have molded its surface. Additionally, the presence of long, steep cliffs known as lobate scarps is of particular interest. These features suggest that Mercury has undergone significant contraction over time, possibly due to cooling of its interior. As the planet's core cooled and solidified, it shrank, causing the surface to buckle and crack, forming these dramatic cliffs. The size and distribution of these lobate scarps provide critical insights into the thermal history of the planet and its tectonic activity. This ongoing geological evolution raises questions about the nature of similar features on other rocky planets and moons in the solar system. The intricate relationship between Mercury's core and its surface is another area ripe for exploration. Studies suggest that Mercury has a large, metallic core that may be partially liquid. The core's dynamics could play a vital role in generating the planet's magnetic field and influencing its geological processes. By investigating how Mercury's core interacts with its mantle and crust, scientists can better understand the conditions under which terrestrial planets form and evolve. These investigations extend to theories about the formation of Mercury itself, including hypotheses regarding how the planet lost a significant portion of its original crust and mantle, leaving behind a dense metallic core. Moreover, understanding Mercury's environment enhances our comprehension of planetary atmospheres in general. Despite its proximity to the Sun, Mercury possesses an extremely thin atmosphere, often referred to as an exosphere. This exosphere consists of trace amounts of oxygen, sodium, hydrogen, helium, and potassium, and it is continually being replenished by solar winds and micrometeoroid impacts. The dynamic nature of Mercury's exosphere makes it a fascinating subject for research, offering insights into how exospheres function on other celestial bodies as well. As we delve deeper into the study of Mercury, the potential for future discoveries looms large. The upcoming Bepi-Colombo mission, a joint venture between the European Space Agency, ESA, and the Japan Aerospace Exploration Agency, JAXA, is expected to provide a wealth of new data about the planet. Scheduled for launch in 2018, Bepi-Colombo will consist of 2 spacecraft, the Mercury Planetary Orbiter and the Mercury Magnetospheric Orbiter, designed to explore various aspects of Mercury's environment, surface, and internal structure. This ambitious mission aims to unravel some of the remaining mysteries of Mercury and is anticipated to yield groundbreaking insights into its geology, magnetic field, and exosphere. Bepi-Colombo's sophisticated instrumentation will enable scientists to conduct high-resolution imaging, spectroscopic analysis, and magnetic field measurements, facilitating a comprehensive understanding of Mercury's composition and processes. By utilizing advanced technologies, the mission aims to address key questions about the planet's formation, its evolution over time, and the factors that contribute to its unique characteristics. The anticipation surrounding this mission reflects the ongoing quest for knowledge and the excitement of uncovering the mysteries of our solar system. The implications of studying Mercury extend beyond planetary science. They touch on the fields of astrobiology and the search for extraterrestrial life. By understanding how planets like Mercury form and evolve in such extreme conditions, scientists can better comprehend the potential habitability of other worlds, particularly those within the habitable zone of their respective stars. The extreme conditions found on Mercury highlight the diverse environments that exist within our solar system and challenge our preconceived notions about where life might arise. In addition to planetary science, the exploration of Mercury has implications for future space missions. Understanding Mercury's surface and its interactions with solar winds can inform mission designs for landers and rovers on other celestial bodies. Lessons learned from Mercury can be applied to the exploration of asteroids, comets, and even the icy moons of the outer solar system. The experience gained from studying Mercury's unique challenges can aid scientists in addressing the complexities of other worlds. Beyond the scientific realm, Mercury captivates the imagination and inspires curiosity. Its status as the closest planet to the Sun sparks interest in not only the scientific community but also the public. The mysteries surrounding Mercury resonate with our innate desire to explore the unknown and discover new frontiers. The allure of space, combined with the advancements in technology and our expanding understanding of the universe, fosters a culture of exploration that inspires generations. The fascination with Mercury also encourages discussions about our place in the universe and the nature of existence itself. The quest to understand Mercury and other celestial bodies prompts us to reflect on the origins of our solar system and the processes that have shaped it over billions of years. These reflections extend to philosophical considerations about the potential for life elsewhere, the nature of consciousness, and the significance of human exploration. In a broader context, the study of Mercury can serve as a metaphor for humanity's journey. Just as scientists tirelessly unravel the mysteries of this enigmatic planet, individuals seek to uncover their paths in life. The challenges faced in understanding Mercury mirror the complexities of human existence, where curiosity, perseverance, and a desire for knowledge drive exploration and discovery. As we continue to push the boundaries of knowledge and venture into the unknown, the mysteries of Mercury will remain a focal point of inquiry. The ongoing research and upcoming missions promise to deepen our understanding of this fascinating world and its place within the cosmos. The journey of exploration is a testament to the human spirit, a quest for understanding, a desire to connect with the universe, and an acknowledgement of our shared existence among the stars. The narrative of Mercury is still being written, and each discovery adds a new chapter to our understanding of this planet. As we look to the future, the mysteries of Mercury will continue to captivate our imaginations, encouraging exploration and inspiring new generations of scientists and dreamers. The journey of discovery is far from complete. It is a dynamic and evolving process that invites us to participate in the grand adventure of understanding our universe. In conclusion, Mercury, with its remarkable characteristics and myriad mysteries, serves as a focal point for exploration and inquiry. Its extreme environment, unique geological features, and the complexities of its atmosphere offer valuable insights into planetary processes and the evolution of rocky planets. The ongoing research and upcoming missions will undoubtedly deepen our understanding of Mercury and its place in the solar system, inspiring curiosity and fostering a spirit of exploration that transcends boundaries. As we continue to unravel the secrets of Mercury, we not only gain insights into this enigmatic world but also embark on a journey that connects us to the cosmos and the mysteries that lie beyond. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.